Monday, we learned about neural networks. Neural networks are not much more than a bunch of matrix multiplies along with a bias term, except that we can't just have a bunch of layers composed of that, because we wouldn't get any nonlinearity, right? If we composed a bunch of matrix multiplies plus adding some bias, that'd turn into just one big matrix multiply plus add a bias. And so we need to throw in nonlinearities into the equation there. Before I go any farther, a couple housekeeping notes. One, Jack, when I call your name, and everyone, you have an option that I never mentioned to you, but I'm mentioning now, and that is pass. Okay? So you can always say that if you need to. Okay? Having said that, I think it's good for you to just try, even if you're not sure, but that's okay. So pass is a valid option. Does that make sense? Any questions? Second, office hours. I did add another office hour on Monday before class. So basically it's Monday before class and after class. Tuesday I am usually on campus and we can arrange to meet. So I have clinic stuff, but I'm usually available an hour before 11 and usually from noon to 2, let's say. So feel free to contact me and arrange that. That's two things. A third thing is assignment 2. So many of you, I think, tried to get access to the leaderboard and couldn't because you didn't have access. So two things. One, I went ahead and made access to our Google Groups for this class. So if you are using your email that you signed up for the, your official email, signed up for the class for, you should now have access. Otherwise, I should have provided access to everyone who asked. So if not, send me another access and I will try and do that quickly. I just wanted to show you what the leaderboard looked like. Basically, you put your name and how long it took to train your model and what the validation loss was. So here, for example, Josh put in 2 entries. One, which clearly had a small number, quick training, so 1.99 seconds, and then one which had a lower loss. And so the leaderboards are here. So Josh actually is in the lead for both, which is not surprising because he hasn't had much competition yet. So go get in there and do better than that. Do make sure whatever your entries are here, go ahead and put them in your assignment, in your notebook, so that I can just see what the settings were that you used, because that'd be of interest, and I'm sure to be of interest to everyone else. So we'll talk about that on Monday. And the last thing is, for the assignment, you should be submitting the assignment, and I know this is different from the first assignment. So you should be submitting the assignment with edit privileges for me. I promise I won't go and ruin your notebook. I should just comment on it. But please do provide me edit privileges. And also remember, just don't make any changes after 11 p.m. tomorrow night on that. Any questions? Jack?
Sorry, I heard this, but are there, for the little homework assignments that we do, are there solutions posted for those, or is that just?
There are not solutions posted. Is that a request?
I think I can just ask specific questions in office hours.
Is anyone else, would that be useful to people? Okay, then I will do that. Next Wednesday, I'll be handing out the midterms, which you work on until Monday when you bring them back. Doesn't sound quite right. So it's like an hour and a half or 2 hour midterm. You'll find a block of time and do it, as opposed to work on it the entire time from Wednesday to Monday. That Wednesday will be a review session, so a week from today. So please come with questions, okay? I will try and come up with sort of a sketch of outline of what we've done, but it'd be much better to be question driven, right?
Is the midterm going to be more like theory like this, or is there a coding part too?
There certainly won't be running any code.
Like there's not a collab notebook.
There's no collab notebook. No, no. It'll be no. All right. All right. So I wanted to go through and look at a neural network in a little more detail, and in particular look at the presentation that we saw at. We don't need this anymore. So at the end of class on Monday, we talked about the alternate way to look at a neural network, which is actually as a network here. So the first way we looked at was in terms of functions that we were defining, either an xw plus b, so multiplying some input by a matrix and adding a matrix to it, or then a nonlinearity. The nonlinearities we looked at in our internal layers, which are normally called hidden layers, is normally ReLU. Okay? And then the output activation function, or nonlinearity, depends kind of on your loss function, what you're looking for. It's going to be kind of related to what sort of a y hat you're looking for. So sigmoid if you're looking for a probability, softmax if you've got a set of probabilities to sum to 1, a set of sigmoids if you've got multiple probabilities. You might have just a identity function if you're trying to come up with a regression for a number that could be anywhere between negative infinity and infinity. So what I'd like to do is go through and use this network, and let's just work through it a little bit, first in what we call the forward pass. So the forward pass is, you're given an x, you know all the weights, you know all the biases, which aren't here. So in this particular example, I'm going to assume the biases are all 0. And you want to come out with your y hat. Okay? So that's part 1 of what we need to do. We can't come up with a loss until we know a y hat. And then the second thing we're going to do is go through and do a gradient descent. And that will normally be called a backward pass. So we'll normally be moving forward to compute the y hat, and then move backward through to compute the gradient for every one of the coefficients. That is, every one of the weights and every one of the biases. No.
Does that networks like that usually only have one y hat, or do we merge all the y hats together in the last round?
We don't merge all the y hats together. This happens to be a single y hats of 1. We could very well have multiple of these, and they would all just feed into the loss function. Okay? Other question? Or questions? I am going to quickly add in some biases, I think. So for this picture, where would a bias go? Anyone? Jack?
Possibly in the summation.
Yeah, this is so because this summation is summing the arrows basically coming in, the weighted sums here, and adding in a b. So let's put in, let's say, a b sub 1, and I'm going to just give it a value of 0. And I'm going to put in here a b sub 2 with a value of 1, and a b sub 3 with a value of 1, and a b sub 4 with a value of 2. Okay? And this is the part where I'm going to need you guys to all stand up. So we are going to play network. Okay? Everyone, so you're going to assign a role. X's are roles. Each W is a role. Each part of the layer function is a role. So the weight multiplication is a role, and the activation function is a role. And someone gets to play the loss function. All right, so step right up, and I will hand you a role. And what you're going to do is sort of stand by your part of the network. So these guys, A's will be, A will be here, C will be here, and then B will be next to them, and D will be there. And so the weights guys are just have to figure out a place to be between the X's and the A's and C's. All right, stand up, step up. And some of you are going to have extra information on your role. So, Oh, don't take 2. This is a boring one. We'll see whether that's less boring. And if you can't read my writing, please let me know. Okay, try and spread out to some extent, like the x's should be way down there. Oh, no x's have been created yet, sorry. You get to be 2 x's, okay? So you're way down there. And I am going to be j because it's a very simple roll. So we are going to, this would be better if it were spread out. So, all right. So we're going to go through and do these calculations, all right? So we're going to do the calculations, like if you're A, are you A?
I'm not.
You must be a weight. No?
No.
You're D? So ready? This is going to be closer to the board. The top is closer, and the bottom is farther away. All right. So your B should be right next to you there. You B? All right. And you're, oh wait, and you're D. So E, sorry, yours D. Where's C? So C and D should be like right next to each other. There we go. Across from A and B. All right. A, do your thing. So what do you need to do to find out your value?
Get the weights in the B,
And
add them.
go ahead.
Where are the weights in the B?
Which weights do you want? Ask for them by name.
I want W1, W3, and B1.
A B1 actually is non-animate.
Okay.
So
So then W1 and W3.
I'm 1.
and you are?
1.
Okay. Your sum is?
2.
Nope. Can anyone help him out?
Oh.
So what you're summing is the weighted sums of these.
Okay. So then X1 times W1.
Yep.
Okay.
So
X1
X1
is
is,
2.
yeah.
W1 is 1.
Help him out.
Yeah, 1. Sorry.
Okay. So 2 plus 3, 5.
That was your cue.
So 5.
5? Does everyone agree 5? All right. You remember 5 for a second. C, do your thing.
We're going to still be 4.
Ask for him. They'll tell you.
You're -1 and then 1. So we have x1, which is 2 times 1, plus x2, which is 3 times -1. So we have -1.
-1. Okay, and your bias?
We have b2.
B2 is right here.
Okay.
Sorry. You're at -1 right now?
Yes.
Okay. B2 is -2. Okay. So your total is, you had the bias, -3. Okay, you are?
5.
And you are? All right, now, let's just look at that in matrix form right here, okay? Our matrix form is X times W plus B, right? So let's just kind of look at that. What's the X? Go here. Here, Mr. X, Mr. X's. Enter yourselves on the matrix. Okay, and we know that we're going to equal, we have 2 values at the end, right? So we know we're going to end up with a matrix 1 by 2 or 2 by 1. So our input is a 1 by 2, right? So we have 2 inputs here. The outputs should be the same form. So therefore, if this is 1 by 2, this is going to be 1 by 2, okay? Enter yourself where you belong in here. 5, all right, and? -3, excellent. And I'm going to go ahead and do the b's, because b's aren't here to talk for themselves. So those are 0 and -2. W's, step right up. So what W are you?
1.
You're 1. And why are you putting yourself there?
Because I want to be multiplied by the 2.
Okay, but why aren't you over here?
Because I want to go to the
Because he belongs on the
Go to
left,
5,
because he's the top one. Does that make sense? Okay, next. So W2, you're going to be in the left column or the right column?
I am going to be in the right column,
Okay, top or bottom?
bottom.
Okay. Next.
So, let's see. I multiply by x2, and then I go to a. So, I think math is hard. I think I go right here.
All right, let's just see if this makes sense. So if I do this matrix, it was like 2 times 1 plus 3 times 1 is 5, plus 0 is 5. We're good so far. There's only one place left. Okay, so you trust everyone who's gone before you, and you're, by the process of elimination, going to put yourself in.
I think I actually go here.
You think you go there? Okay.
Yeah.
Let's think of why. So, do you get which one are you? W. You're this guy. So do you get multiplied by x1 or x2?
x2.
X2. So therefore, you belong there. I agree.
Sorry.
And are you -1? Okay. So where do you belong?
Above.
Above, because you're multiplying by x1. All right? Does this make sense? What do we call, so we call this x, or I'm going to call it a at 0. What do we call this? Matrix. W, which W? Which layer? We're going to call this one actually layer 1. Okay, so this is layer 1. Plus, what B is this? 1. And that equals, put it down below. Can you remember what it's called? Z. This was Z at 1. Okay? So that's what's coming out of the first function in the layer 1. All right. Who do you need to pass your information off to?
To B.
Yes, where's B should have been standing right in front. Okay. So what are you telling him?
5.
And what do you do?
And then have to pass it on to the next.
Well, yeah, but your ReLU. Do your special ReLU sauce.
Oh, God. What was it again? I forget.
I'll give you a picture.
Sorry, I forget.
So this is y equals x, and this is y equals 0. So if you're less than 0, you spit out 0, and if you're greater than 0, you spit out x. So you got given,
5.
and you spit out?
5.
Good job. That's your special sauce. Okay, so you got 5 coming out here. All right, so let's fill this in here. So A at 1 is equal ReLU of Z at 1. So you write yourself in.
So I just write 5.
Yep, sounds good. All right, and you were -3. Pass that on to your,
0.
all right, oh, you already, go ahead, write it in, 0. Right, so we have 5 coming out of here, and we have 0 coming out of here, and we put them together in our vector there. All right, let's go on to E. Are you E? Who's E? All right.
Yes.
So ask for the weights and they will appear.
Where is W5? Here. Where is W5? 2. Alright, so I want 2 times 5 plus 0 times something. I guess W6, what are you? 3. 3, I don't care.
Exactly. Exactly. Okay.
Okay. So, do I write
Just say it.
Okay, so I'm going to ask again what W5 was because I forgot. 2. 2? Okay, so 10
What are you missing?
plus 1.
Excellent. Okay, so you're 11, right? So, and G? Go ahead.
What are, who are W6 and W8? W6.
3.
3.
How can she be that, how can she be west of you? It doesn't make sense. Go ahead.
So we did our second term is 0, so unfortunately W8. Care about you. So we have 15, which is 5 times 3, and we also have our bias, which is 2, so 17.
All right. Who would like to do this for me? Fill this all out. Or fill in your parts. Here you go. Okay. And we're going to be checking this afterwards. And of course, we'll need B and D back in too. Oh, and I play the role of B. I better hurry over there. So we're missing 3 actors.
Can you have it?
And D? Let's just make sure 5, 10, 11, 15 to 17. All right. Quickly finish this off. So who's I? Go ahead.
Where's W?
-1.
Oh, wait. Did F and H need to do their thing? This is a very important part, yeah. So what are you going to do? Okay.
Yeah, same.
Okay, so you're taking 11 to 11?
11.
And you're taking 2, 17. All right. What's the name of this? Z2, right? What's the name of it after you guys get done with ReLUing it? A2, right? So A2 also equals 11, 17. I'm sorry, now I can go. Was it you or you, I?
Yeah, I'm
Go ahead. Do your thing.
-11, there's no B. Right? There's no B.
Oh, yeah, B. 0.
11, and then where's the 1? So -11, 17.
Your total is?
6.
Okay, and you pass it on to ID, which is me, and I just do the identity, so I'm even less interesting than ReLU. So you said 6? So 6. So Y hat, I spit out happily, is 6. Who's the loss? Okay? Oh, you don't know what Y is yet. Y is 4.
Alright, so I'm 4 minus 6 squared, which is 4.
Okay, so that's the loss. This way of doing it, with all the little arrows and stuff like that, is, I think, a pain in the ass. Okay? I think this way is much more straightforward. But whichever way you want to think of, actually, you should be able to think of it both ways. Okay? Questions right now? J, ID is the identity function. G of x equals x. So for something like a regression, that might be a reasonable thing to do. I certainly didn't want to be, sigmoid's too hard for me. So I gave myself an easy one. Okay, so if we want to be estimating, I don't know, I was going to say house prices, but there maybe even still you'd use a ReLU. There's no reason to be predicting negative, right? It just makes it a little harder for the function to learn if it has the ability to spit out negatives. So we kind of take that last function and force it into what seems like a reasonable range for our values. All right, that's enough for now. Have a seat. We may be coming back to this, though. Take your cards. No. All right, so here's what we get into now. We know how to do the forward pass. We know how to calculate y hat. Now we need to update the coefficients. How many coefficients do we need to update here? Let's see. So we got 4-way tier, 4-way tier, 2-way tier. That's 10 plus 5 because biases. Yeah, there's a bias in every one of these. So we can either be counting each one of these and saying, yes, there's a bias, or we could just look and say there were 2 biases here, 2 here, and 1 here. Okay, so we got 15 coefficients, yeah.
What were we initializing every coefficient to?
Everyone can tell you what their coefficient was initialized to. They all had values. I picked them to have interesting things that would happen. So I wanted to make sure some ReLU once got to cap something off at 0. But we can imagine we just did a random initialization. We can imagine we've been doing gradient descent for a while, and this is where we got to. Doesn't really matter. So we need to update weights. We know the chain rule. We know how we use that for updating our polynomials. And it's going to be sort of the same. So if we look, for example, at weight 9, okay? We look at I, J is the identity function, so we're going to ignore that, right? Because the derivative is just 1. But if we look at this, right, this is basically I is equal to I'm going to abuse a little notation here. I'm going to just use these letters since we happen to have them. So I'm going to say F is the output of this node, right? Another name for that is A2, the first element of A2, right? But I'm going to just call it F. So it's W9 times F plus W10 times H plus my little b here, B3, B4, B5. Do we know how to take the derivative of this thing? Yeah, so we can take the derivative of this with respect to y hat. We know how to calculate that. I'm just looking for my colored chalk. By the way, you should know your Harvey Mudd, where'd it go? Anyway, your Harvey Mudd tuition goes to buy us the finest chalk that exists. This is special Korean or Japanese chalk. I don't know, but it's pretty cool. So we know how to calculate this derivative. We know how to calculate this derivative, because it'll just be 1, right? Because it's just the identity function. what is the calculation of that derivative? With respect, I'm going to put it halfway there, because I really just want it to go to W9. So with respect to W9, what's the derivative of I with respect to W9? Yeah. So the derivative of this is f. That is, it's whatever this value is coming out here. Let's just see if that makes sense. So we would multiply together this derivative times this derivative times this derivative to get the derivative of the loss with respect to W9. So what does that mean? That means if we increased W9 a little bit, what sort of an effect would it have on the loss? So we would have I'm going to come over here. So we have the derivative of the loss with respect to W9 equals derivative of the loss with respect to y hat, which in this case is j, right? Times the derivative of j with respect to I times the derivative of I with respect to W9. This one is equal. It's 1 because this is the identity function. So f of x equals x. In this case, it's a g because it's an activation function. G of x equals x. G prime of x equals 1. The derivative of L with respect to j is 2 times y hat minus y, I think, right? We've done this over and over again, right? So because of the chain rule, we'll get another negative out of this, which will flip the order. Yeah.
Can you explain a little more? I'm confused about taking the derivative with respect to j in a sense.
Sure.
Because that's with respect to y hat.
J and y hat, right? The output of j is y hat. So same thing. Same thing. So this one is going to be 2 times y hat minus y, right? And y hat is just j. They're kind of one and the same. Hardly we could, which is also equivalent to 2 times j minus y. And we know j because we calculated it on the way up. And then the question is, what's the derivative of I with respect to W9? Well, if this is the equation for I, everything else in this equation we can treat as a constant. So therefore, the derivative is just going to be f. How do we know what f is? We should probably remember that as we're doing our computation. We don't have to go from the beginning and recalculate what f is, right? So as we're doing our calculation of our y hat, we should be saving every a and z value so that we can do this backward computation. So this is conceptually what we need to do. Does it make sense? All right, so that will tell us that in this particular case, see, this is where we're going to go back. What was y hat? That is, what was j? J was 6. So this is 2 times 6 minus, and y is up there, right? 4. Times, what's the value of f? Who was f? Your value was? 11. So 2, 4, 44. So very positive. So what do we need to be doing to that weight? We need to be decrementing it, right? So the claim is if we decrement it, we are going to reduce the loss. And does that make sense? If we decrement the weight, what was W9? Negative 1. So if we make it, and what was F? 11. So if we make W9 smaller, I is going to be smaller. I guarantee you j is going to keep it smaller. And loss, what's going to happen if we decrement? What was y? 6? Or y hat? Y hat was 6, and now it'll be a little smaller than 6, right? So loss, are we doing better or worse? Better, right? We've reduced the loss. Okay, so that makes sense, right? I think, any questions at this point? Now, the problem is, what if we look not at W9, but W1? All right, so we're here. What does we had basically a path from our loss in our network back to the weight of interest. And we calculated the partial derivatives along the way and multiplied them together. What does the path look like to W1? Go ahead. There are multiple paths. What do we do? Well, here's how we got to, let's imagine we're at W1, and I'm considering bringing you back up here to do this. Let me just see if we talk about it, whether it makes sense. So we have W1. Let's do some numerical differentiation here. So let's just add an epsilon to W1. Who's W1? You're W1. Okay. So what's your current value? 1. So let's make it epsilon, where epsilon is 0.5. It's a giant epsilon. Actually, epsilon is 1. So you're now 2. Who are you going to affect? You're going to affect it. Are you going to affect C? C doesn't change. So A, raise your hand. Okay, A, who are you going to affect? B, raise your hand. B, who are you going to affect? E and G, raise your hand. E and G, who are you guys going to affect? F and H, raise your hands. You're not F and H, I know that. Who's H? Okay, thank you. You're going to affect I. You're going to affect me, which is J, and J is going to affect the loss. So raise your hands if you just raise your hands in any part of this process. All right, there are a lot of nodes that are affected, right? And for A or for B, there was only one path from the weight to here. But if we look, for instance, at I, we can get there in multiple ways, right? We can get there from A across here and across there, or we can also go down here. Now, if we think about making this change, where we increase W1, that is going to either increase or decrease E, depending on what this weight is, right? And either increase or decrease G, depending on what the weight is. And then depending on these weights, it's going to go ahead and make a change on this one, which is going to make a final change on the loss. But they're additive. If we want to look at the change in the loss, we could just look at the first path and find what the change is, and add that to the change in the second path. We can do the same thing if we are looking at the derivative. We can say the total derivative from this loss to this weight is using the chain rule for all of the different paths that you can get there from. So I'm going to say that partial L to partial W1 is going to be equal, and let's just look at our path of how we get here. Our paths. So the first path, let's go along the top. Okay? So we've got, and I'm going to need more room for this. So L to, what's the last one is? J? To J, J to I to what? to what? And here's the key. When we're going along this path, we don't care, and I understand why you said that, because that's what we just had. We don't care about the partial derivative from I to W9. We care about the partial derivative from here to here. That is from I to F, because we need to keep going all the way back. So we're going to go I to F, F to E, E to B, B to A, and finally A to W1. That is a component of the gradient from L to W with respect to W1. Then there's another path, plus, and parts of it are going to be the same. L to J, J to I, but now we change, right? So now we're going to take this bottom path down here, so it's going to be I to H. H to G. We don't care about this one because there's no way to get from W1 to there, right? So we're not following that. But now we go G back up to B. B to A to W1. Since there are only two paths, we only have two components here. That would be our total gradient. How many paths might we have in a network? Yes, that's the technical term is a lot, right? We could have, in fact, if we just had this hidden layers with two hidden layers like this, and we had n of them, approximately how many paths do we have to get to one of the first weights? 2 to the n, which sounds a lot like exponential, right? Which is not what we look for in our algorithms. So we have an exponential number of paths that we need to calculate these partial derivatives of. So we're not going to do it. We're not going to implement it this way. We're going to end up with the same value, but we're going to take advantage of the fact that we have to do a lot of recalculations, right? We are going to need to know, for instance, the derivative of L with respect to I for every one of those weights that are going from this direction. We'll call it downstream, right? All those weights you're going to need to know partial derivative of L with respect to I. All the ones from here on, we'll need to know the partial derivative of L with respect to E, for example, and partial derivative of L with respect to G. And so we are going to use dynamic programming to ensure that we don't keep recalculating the same thing over and over again. All right? Does that make sense? Any one of these particular derivatives is very easy. Let's look, for instance, at the derivative of I with respect to F. Okay, right? Let's do I with respect to H, just because I have more board space here. So we knew what the derivative of L with respect to J is, right? It was 2 times J minus Y, I believe. The derivative of J with respect to I was 1, because it was the identity function. What about I to H? We know what I looks like, right? Looks like this. So what's the derivative with respect to H? W10. Right? So when we're trying to find the value of the gradient with respect to a weight, the previous input is a constant. But when we're trying to compute the derivative with respect to the previous value, then the weight is a constant. Okay? But in any case, this would just be W, what is it, 9? 10. This would be 1. This would be 2 times j minus y. Let's just do the rest of these, h and g. So from h to g. So this is the ReLU function, right? H, what was your value, by the way? Your value is 17. So therefore, if we look at his graph, he was over here on the positive side. So what's the slope? 1. So his slope is 1. So in this case, this derivative is 1. However, what else could the derivative have been? In fact, who was this guy? Was this guy that didn't make it? No, this one. Who's D? Your D? So what was your output?
0.
0. What's your derivative?
0.
Right. So D to C is going to be a derivative of 0, but all the rest of the ReLUs that didn't cap it off will have a derivative of 1. We'll get back to that concept in just a moment. Let's just fill in the rest of them just for fun. G to B. Anyone? So G to B. W6. Yeah, that nice looking 6 there. Times W6. Times B to A. Who was B? What was your value and what was your slope? 1. Sounds good. And A to W1. This is just like before when we were going I to W9. And we said it was the output here, right? Because the W9 is a variable, and the thing it's multiplied by is the constant. So in this case, A calculates by doing x1 times W1, right? So therefore, when you take the derivative with respect to W1, it's x1. So this is x1, which equals 2. So our total derivative is 2 times whatever W6 is, times whatever W10 is, times 2 times the difference here, which was what? So this is 4 times W10 is 4 to 60 W6 is
3.
So I think that was 16 times 3 is 48 times 2 is 96 or something. All right? So therefore, we want to reduce W1. What would happen if we had gone through this node here? Right? Like let's say we were trying to calculate W2 instead of W1. We would have gone through this node. What would the derivative have been? 0. Why 0? ReLU gives you 0 here, right? The only way to get to W2 is from C, right? And the only way to C is from D, right? But what's the gradient from D to C, the partial derivative? Is 0. So no matter what we have up here, it all just craps out here. And we get a 0, and we don't make any modifications to W2. This is called vanishing gradient. Well, it's one use of the term vanishing gradient. So the vanishing gradient has this idea that as you have a deep network, you're doing a lot of multiplications, right? If any one of them is 0, the gradient goes to 0. We are doing a lot of multiplications and then multiple sums of multiple multiplications. So basically what we've got is a we have a big summation, right, within a product within that. This large product, whose length is dependent on the depth of the network, could have zeros, and if there's any 0, it cuts it out. Or if the average gradient, let's say, as we were going through, were, let's say we used sigmoid for each of these instead of ReLU. If we look at the sigmoid function, right? It's like that. What's the slope when it's really negative? 0. And when it's really positive, it's close to 0. In fact, the maximum slope is 1/4. So let's say you had a bunch of derivatives you're multiplying together, and at every layer, you have something that's no bigger than 1/4. You're going to have an error here. It's going to get sort of 1/4 smaller, 1/4 smaller, 1/4 smaller, 1/4 smaller. Pretty soon you're talking about real exponential shrinkage. That's really what vanishing gradient is. So part of what has made deeper networks possible is choosing better activation functions so that we don't get this vanishing gradient. We'll talk about vanishing gradient a lot. One thing to keep in mind on the vanishing gradient is if you've got a bunch of paths, as long as some path is not 0 or close to 0, you're still going to get some gradient to that location. We have another potential problem. What if we chose a activation function whose average value was not less than 1, but was like 3? So we had a path through here where we had, let's say, from here to here, the gradient was, the derivative was 3. Yeah? Explode. That is, in fact, the official name for it. Exploding gradient. So that's why we don't like to have large derivatives. Because large derivatives, if you multiply them multiple times, get really big. And you can get overflows. How many of your multiple paths need to explode for your total gradient to explode? Just one. Any single path that explodes kills you. There are some approaches we're going to look at to deal with exploding gradients. All right, but just know that it's a problem. And from this picture and the multiple paths, kind of see the problem. The multiple paths, the fact that basically you're multiplying by the derivative of each segment of the path, and that can be very long. Right? Yeah.
Could you explain again why it explodes when there's one path going wrong? So, yeah, it seems like it would only affect that path.
It would only affect that path, but what if one of them, what if you get overflow on one thing and you sum that with a bunch of other things?
Yeah.
That's the problem. Okay. Not only do you have to worry about your activation function, if we look at what else is involved here, what do we have here? A weight. What do we have here? A weight. What if the weights start getting big? Right? Forget the activation function. Just the weights start being big. Then all of a sudden, as you move from the loss function back and back and back and back, you're getting an exploding gradient. And conversely, if the weights are small in a path, you're going to get a vanishing gradient. So it's this careful kind of balance that has to happen for this learning to actually work. And for a lot of years, two-level networks were about what could be trained. Okay? And it wasn't simply a matter of computational power. It was the fact that they didn't know how to do initialization, how to choose appropriate activation functions, other things. Was there a question here?
I guess,
Check.
So really works out nice because it doesn't get too big or too small. That you're either going to have a 0.
Well, you can have the 0. And like if we look at that one, like here, we have the 0. We're just not going to be able to update W2, right? So it's only if we get for this particular input, we're just not going to be able to update this. We'd have to get some different input that would cause this to go positive, such that the ReLU wouldn't take effect. That's why the leaky ReLU is an alternative, such that at least you have some small gradient in that other direction. It's different. So on Monday, we're going to look at the dynamic programming approach to actually calculate all this using matrices. Right now, what I wanted to show you was just another training. Right, so we looked on Monday at training what were we training? We were training, help me out because I really don't remember. Oh, we were looking at, yes, MNIST. So we were trying to do multi-class classification. And I'm going to assume this is going to come up shortly. So what we're going to do today is look at, and this is again from the Cholette book. We're going to look at classifying movie reviews. So there's a bunch of IMDb movie reviews, and we're going to basically say, was it thumbs up or thumbs down? That is, we're given ones or zeros, and we're trying to predict. So this, like the one on Monday, has been adjusted so it works with TensorFlow 2.0. And IMDb dataset, 50,000 positive and negative reviews. Half positive, half negative. That's a good thing. If we had 10% positive and the rest negative, then we'd be biased towards predicting negative, right? In fact, if you just predicted negative all the time, you'd be 90% right. So that's why it's important to have a balanced training set. And so IMDb, you could just load this in automatically. The 10,000 words tells you of all the distinct words in the reviews, it'll keep the top 10,000 of them. So if you imagine among reviews, there might be lots of different words that are used. I'm going to erase this and show you how we're going to represent a review. So the representation we're going to use is called bag of words. Here's the idea. You take the words in the review and if we look at it from a Unix point of view, we take our words, we pipe it to sort, we pipe it to unique. If this looks familiar, that's great. If not, I'll have to explain it. So we just sort all the words. We totally lose their relationship to one another. Right? If the original review is this is a piece, and who knows how it continues, then we're going to just get A is piece this. Okay? We're going to throw away multiple of the same word. So bag of words, basically we keep track is of these 10,000 words, which of them are in our review and which aren't. And the way we're going to represent that is what seems like the stupidest way. Right? So we're going to have 1 to 10,000, and we're going to just have a 1 or a 0. So we might have a 1 here, and this is the word is. And we might have a 0 here, and this is the word hilarity. I don't know, whatever word is not in there. So we have all 10,000 words. Yes?
So we traverse the whole data set first to find most common ones, and then we have this.
Yeah, that's this load data goes ahead and we'll figure that out. So it goes ahead and figures out the most common words. It probably pre-computed, I'm not sure. But simple matter of programming to do that. Question so far?
What is the 0 again?
0 says this word is not in this review. So there's 10,000 entries in this vector.
Each entry is a review.
Each X here is a review. Okay. Yes, this is a review. So this is an X, and Y is equal, let's say this is, you think positive or negative review? I'm going to say negative for this one. All right. So the input is a 1 by 10,000 vector.
Okay, and so for each review we're saying like, is these 1,000 words, are they in this review or not? Okay.
That's it. Yep.
It's just a binary 1 or 0 now that's in bag review.
1 or 0. Is it there? Is it not there? That's right. It's called bag of words. It should really be called set of words. Because in data structures, a bag usually represents a set that has you can be part of multiple times, so there's actually a count. Some people would use that as a slightly different one. So we use the word is 10 times. That'd be a true bag of words. In our case, this is a cut down bag of words. All right, and then this is training data 0. So it's I'm just checking something here. Why is this not 10,000? Oh, I see. I take it back. So the loading the data set, when you load the data, it still keeps the words. We haven't yet done the sorting part in the bagging. So this is just converting each word to an associated index. So we have a dictionary of all of the words and the index of each one. Okay? And then, come on, we go ahead and vectorize the sequences. So this is really going to do that. It's going to go ahead and set the results for a particular one of these is the index of the word we're looking at, and one of them is which training sample are we looking at. Okay, and so it'll basically be setting to 1, the rest of them will be zeros. So we got this giant data set. Now let's actually look at, so here's a particular training set. We've got some 1s here and some 0s other places. All right. So let's look at what this is basically what our network is going to look like. So we're going to have a size 16 at the first hidden layer, size 16 at the second hidden layer, and then one output. We know the input is going to be 10,000 big. So we'll take it basically 10,000 down to 16, another 16, both of those ReLUs, and then an output sigmoid. So you might say, how well could this do? And the answer is pretty good. So first off, we have an optimizer RMS prop, binary cross entropy, right, which matches what we want to be doing. And if we train then, we get a loss that goes down. Fine. We don't know exactly whether the loss is good or bad, but we can see, so when we call this, we get back a history. So we can actually create a graph or something like that. And so we can see the graph and look at the accuracy and see basically this is our training loss and validation loss. Okay, training loss and validation loss is interesting. We can see we're beginning to overfit, right, as we're starting to go up here. So somewhere in this number of epochs would be better. But let's really look at the accuracy. That's what's important. And just this takes like 20 seconds to run. And here's our accuracy. So we're just under 90%, like 88%, for basically running for under a minute on 50,000 samples with these 10,000 input vectors. Not bad. How many coefficients do we have? How many parameters? At the first layer, from the input layer to the first layer. Not 16? How many inputs do we have? 10,000 to 16. So 160,000 in the first layer, and then 256. And then what was it? Another 256 and 16. So pretty much dominated by that 100 and however many it was, 160,000. So that's it. Deep learning can work well. Here's an example. We're going to look at lots of different examples of how you structure things, because that's going to be a big question for doing deep learning, is how do we structure our input to actually make this work? How do we come up with a loss function? Have a good weekend.